Welcome everyone to this week's Oxford Discrete Maths and Probability seminar. In a moment we'll introduce the speakers, but before we do so, I just want to make an announcement about next week's seminars. So we're having a special event where the Oxford seminar goes down under, north meets south, so we'll have two speakers in Australia. In order to accommodate the different time zones, this will have to take place in the morning UK time, so you can see the details on the slide that's showing at the moment. So for this week, as usual, we will be recording these seminars, so let me just quickly put up our GDPR statement. So the slides for the first talk are on the webpage, you can find them there now. As usual, we encourage you to ask questions in the chat and we'll either take them live or at the very end. So let me stop sharing my screen so that Gal can. It's a huge pleasure to welcome Gal Kronenberg, working in Oxford, technically in Tel Aviv right now, and she's going to speak to us about what's her title? The maximum length of K-bootstrap percolation. Thanks very much, Gal. Over to you.
Hi. Oh, wait, how do I do it? Okay. Can you see my slides now?
Perfect.
Oh, magic. Okay. Yeah, so I'll talk today about graph-bootstrap percolation and more specifically the running time of graph-bootstrap percolation. And everything I'll say is a joint work with József Balogh, Alexey Pokrovskiy, and Tibor Szabó. Okay, so previously when I gave this similar talk, then I started with all the history of graph-bootstrap percolation, but these days I feel that maybe like a short teaser will be maybe a good opportunity, since we're talking about infection processes and we're in the middle of this huge huge situation. Okay, so just a disclaimer, I'm not a specialist in any kind of diseases or pandemics or coronavirus issues, but I thought it would be a nice teaser. So let's talk generally about bootstrap percolation and not specifically about graph-bootstrap percolation. Let's start with this. So assume that, okay, let's start with what we call the our neighbor bootstrap percolation. So assume we have the world, it's we call it our host graph, it's G. And we know that we have some sites, some people, some vertices that are infected. And we want to ask ourselves, okay, so what would be the next step? Who will get infected? And how much this disease will spread? So we define the following. We need an infection rule for that. We need to understand under which circumstances we infect, like new people or new elements get infected. And in this kind of percolation, we define it as follows. So if I have R neighbors that are infected, then I get infected. Okay, so the new infected set will be all the previously infected vertices with all the new ones that had at least R neighbors. So this is the R neighbor bootstrap percolation on a graph. Let's see a simple example on the grid. Assume that our world is the grid. So this is, I will show the two neighbor bootstrap percolation and assume that this is the infected vertices, the initially infected vertices. And now let's see what happens in the next step. So this guy, you can see my mouse, right? Like my pointer. Yeah. So this guy will get infected, and also this one, and this one, and this one, and yeah, this one. Sorry. Yeah, all the yellow ones. Okay, and now in the next step, we have new ones get infected. So this one, this one, this one, and we can continue this process until it stops. So I didn't finish it now, but just to give you the idea. So the disease will spread until at some point it will stop infecting people according to this specific rule. And then we can ask ourselves many types of questions. Let me just give you some quick examples. So one question we can ask, so under which circumstances or what should be A0, the first infected set, such that eventually everyone will get infected. We want to understand when everyone will get infected in our population. Or another question is, what happens if we don't have a control on the initial infected set, but we take it randomly? So we pick infected vertices randomly, say independently with probability P. So in this case, for each values of P, we will have that with high probability, eventually everyone will get infected. And the type of questions that I would want to focus on today would be about the length, about the running time. So how many, so maybe I don't care, I care only in some cases that if everyone will get infected or not, but I just want to understand when this disease will stop. So how much longer will it take until I cannot fly back to Oxford from Tel Aviv, until people will stop getting infected, and this is so the disease will stop spreading. So this is the kind of questions we're interested in, but we want to consider it in a different bootstrap percolation model, which called the Graph-bootstrap percolation. And in this time we want to infect edges of a graph instead of vertices. So once again, we have, okay, so this is the H bootstrap percolation on n vertices. So once again, we have the host graph, which is our world. In our case, it will be the complete graph on n vertices. And we have the starting graph, so the set of initially infected edges this time. So we have the infected subgraph that we start with, some people that came from China or whatever. And then, okay, and then we need to define the infection rule. When do we infect new edges? So in this case, in the graph-bootstrap percolation, we have this special graph in mind. We have this special structure in mind. And this is the target graph H. And we infect a new edge. The infection rule will be as follows. So a new edge will get infected if it's the only missing edge in our target graph H. Okay, so in step I-1, I will have all the edges that were previously infected, plus all the new edges that adding them will create a new copy of a graph H. Okay, so this is the percolation process that I will consider today in this talk. And okay, and I can ask the same type of questions as I asked before. So what should be the G0, the initial set of infected edges, such that eventually everyone will get infected? Or what happens if I take this initial set to be random, maybe the random graph G and P, for which values of P with high probability everything will get infected? And once again, the question that I want to focus on today would be, when will this process stop? How many steps will it take until this infection will stop spreading? Okay, until we cannot infect new edges according to this specific rule. Okay, so before moving to example, let's talk now a little bit about history. So this graph bootstrap percolation was introduced by Bollobás in like late 60s under a different name, under the name of weak saturation. So let me just quickly define it. So what is a weakly saturated graph? So we say that the graph G is weakly saturated with respect to this target graph H if we can order the missing edges, so the edges that does not appear in G according to some ordering, such that the addition of each edge by its order will create a new copy of H. Okay, so in this case, we say that the G is weakly H saturated, and most times we also ask also for G to be H free, not contain a copy of H. So the graph doesn't contain a copy of H, but every edge that I am adding according to some ordering, and the ordering is important here, otherwise it will be just saturated and not weakly saturated. So the ordering is important here. I have some ordering that allows me to add edges one by one, all of them, such that each edge will give me a new copy of this special graph, target graph H. So let's now see an example. So I claim that this graph G is weakly K3 saturated. So let's see why. I have some ordering of the missing edges. So I can add this edge because it will create a triangle. I can also add this edge because it will add a triangle. Also this one, this one, this one. And now I can add this one because with the red and the blue, it can create a triangle. So the ordering is really important. Otherwise, I couldn't add it. I couldn't add it before. I could add it only after I added this red. Okay, and now I have this one, and eventually I can add all of them. Okay, so this is, so I can add all of them and I get the complete graph. So this graph, this blue graph was weakly K3 saturated. Okay, so let's define the weak saturation number, which will be the minimum number of edges of such graph. So the graph which is weakly edge saturated. And maybe the first and simple example, which I will discuss more later, will be that the weak saturation number, for example, of K3 will be n-1. So clearly, if I take a spanning path, eventually everything will get infected. I can infect it one by one, and apparently this is the best possible. One of the reasons is that the graph needs to be connected, for example, in order to be weakly saturated. Okay, another example will be the complete graph on n vertices. So I want to claim that this graph, G, which is, I have a click here, AR-1, and I have a complete graph here, complete bipartite graph, and that's it. All the rest of the vertices are isolated. So it's the, yeah, so this is the graph. And I want to claim that this graph is weakly KR saturated. And why is that? So every two vertices that I will take here, I can immediately add the edge between them. Why? Because they are both connected to this click of size R-1. So this is actually a copy of KR-1 edge. So I can just add this edge. So this graph is weakly KR saturated, and actually the ordering here didn't really matter, but it's still weakly KR saturated. And it was a conjecture by Bollobás that this is the best option, so that the weak saturation number of KR should match the number of edges here. And this was proved independently in like several really nice papers by Lova, Solon, Frankel, and Kalai. And interestingly, they all proved it using some algebraic methods. And I think that until today, only algebraic proofs are known for this theorem. So they showed that, yeah, so that the number, that the number of vertices in this graph that I showed you before is best possible. Okay, so we cannot find a smaller graph. So this was for the weak saturation number. But as I mentioned before, so maybe this is the smallest graph that is weakly KR saturated. It has only linear number of edges, but somehow we can infect all the new edges really quickly. So the ordering didn't really take part here. I could order it however I wanted. And if I want to look at it as a process, so I could actually add all of the missing edges only in one step, right? So I didn't need the ordering in this case. So yeah, so this is the graph. So we could add all of these missing edges simultaneously. The ordering didn't matter here. So another question that was raised by Bollobás is, okay, to determine maybe not the smallest set, but the set that will allow us to percolate in the maximum possible number of steps. Now, I don't want to minimize the size of the initial set of infected edges, but I want to maximize the length of this process. Okay, I want to make the spreading as slow as possible, like all governments want to do now. Okay, so now let's define it as a process. So now we need to think about this term of Wick's iteration as a process. Okay, so we think about, let me redefine it. So I have some fixed graph in mind. I have the H-bootstrap percolation. So as I mentioned before, I have some starting graph, which is the initial set of edges that are infected, and I infect new edge when it's the only one that is missing in a copy of H in the previous graph, in the graph of all the edges that got infected until now. Okay, so this is the process, and I stop the process whenever I cannot infect new edges. So whenever the process, this process is stabilizes, so this is the stopping point. It can be either the complete graph or not. Maybe I couldn't infect everything and it stopped. But maybe I could. Maybe it stops when we achieve the complete graph. Okay, so let's see an example. Like, let's go back to the example that we saw. So in this graph, as I mentioned before, we already infect everything in the first. We add everything simultaneously. We can add everything simultaneously. Yeah, so I should mention here that in step I add everything. I don't add the edges one by one. I add everything I can simultaneously. So I added everything simultaneously and it stopped after one step. Let's look at a different example. If this is the initial graph, the starting graph, and we want to consider the K3 bootstrap percolation. So let's see how many steps do we need. In the first step, I can add all of these edges to close a triangle. In the second step, I can add all of these edges, and I'm done. Okay, so in this case, it took me 2 steps. So the Wick's iteration number in this case, it's in the Wick's iteration. I will get to it. The length of the percolation in this case will be 2. Okay, so what is the length of the percolation with respect to this target graph H and this starting graph G0? It's just the first time that I cannot infect new edges when the process stabilizes. So this is the length of the percolation, and in the example we saw before, the length was 2. It took us 2 steps. And now I want to define the maximum length, which will be of the H-bootstrap percolation, which will just be to maximize all of the possible starting graphs of this length that I defined it before. I want to find the starting graph that will allow me to continue the process as slow as possible. Okay, the first structure that do this. Okay, so this is now the parameter that I want to consider during this talk, the maximum length. And in the example we saw before, the length of this was 2. Not the maximum length, we don't know. The length with respect to this specific step. Okay, and the question raised by Bollobás in the same paper was regarding the value of this length of the KR bootstrap percolation, when we want to consider the complete graph as our target graph, when R is a constant here, not depending on it. Okay, so this is the question we're considering. So let's see an example with K3, of course. So if we think about a spanning path, so how long will it take us to infect everything? So in the first step, we can infect all of these edges of distance 2. In the second step, we can infect edges of distance 3 and also edges of distance 4, because we have red, blue, and red, red. Okay, so we can infect all edges with distance 3 and 4. And we have this. In the third step, we can already infect edges of distance what do we have here? 6 and 7 and maybe 8, right? And we can continue this. This process, and we get a lower bound of something logarithmic in n. And the question is whether it's possible. And apparently the answer is yes. So this question was studied by Bollobás, Przykucki, Riordan, and Sahasrabudhe, and independently by Matchkin, an unpublished paper. And then they showed that yes, for K3, the log of n-1 is the best possible answer, and the idea for the upper bound is just, yeah, so you saw that for the lower bound, we, so the diameter, in each step, the diameter was divided by 2, and for the upper bound, of course, we needed to be spanning, and we needed to be connected. So this is more or less the idea here. And for, let's see what happens for K4. So let's try to do something maybe similar for K4. So this is an example for K4. So I have this graph which I start with. So these are just copies of K4 connected with one edge which I removed. Okay, so I can add these edges one by one, right? Once I add this edge, I can later add this edge and this edge and this edge and this edge. But once I add this edge, okay, then I can add this edge, but I can also add this edge because I have K from here, and I can also add this edge and also this one and this one, all of them simultaneously. And in the next step, I can add this edge and also all the back edges here. But the thing is that every time that I add new edge, I can add all of the back edges, but no new edges forward, right? So I can add everything that I can, yeah, I make complete graph, but it doesn't affect the new, these new edges. So I need to actually add them one by one, and this will give me a linear lower bound. And the question is if this linear or a linear lower bound is the correct bound, and they show these two group of others that linear bound is the correct bound, but a better one. So they showed that the answer is exactly n-3. And these are actually the only two exact results that we know, that we actually know the value of the maximum length of the bootstrap percolation. And then for other values, they gave some lower bounds. So I wanted to say that we could do the same that we did before, also with only with larger clicks, right? We could consider this kind of chain of clicks, right? That intersect in exactly one edge and remove this edge. And then we need to add these edges one by one. Maybe in some cases we add other edges before, but we will not add edges here for sure until we infected this one. So this will give us a linear lower bound for every KR, right? And then the answer will be whether if it's true for an upper bound, if the upper bound for other values of R is also linear, and the answer is no. So these two group of authors also studied the K5 case, and the lower bound, this lower bound was given by the first one. Matchkin gave a different lower bound, if I remember correctly. So this lower bound was given by Bollobás, Przykucki, Riordan, and Sahasrabudhe, and it shows that it's not going to be linear, it's going to be longer. We have an option, a better option than what I showed you. And actually for every value of R, they showed that it's going to be n to the power of 2 minus this number R minus 2 divided by R choose 2 minus little o of 1. So for those of you who are familiar a little bit with graph-bootstrap relation, maybe it rings a bell, because this looks like the threshold for the graph-bootstrap relation when we start with the random graph, and it is connected because they did use some random probabilistic methods to prove this lower bound. Okay, but this is a lower bound, and the question is what happens with the upper bound. And they conjecture that the upper bound should be subquadratic. So clearly, some constant n square or n squared choose 2 is a trivial upper bound because we can just start with the entire graph. And they conjecture that actually we cannot achieve a quadratic answer. The process will always, no matter how we start, the process will always end in subquadratic steps. So this was the conjecture. Okay, and okay, so we studied also this problem afterwards, and we also showed some bounds. So the first bound will be for the K5 case. So I'll just remind you that here for the previous known lower bound for K5 was 13 divided by 8 minus little of 1, and we showed that it's subquadratic, our lower bound, but it's very close. It's n to the power of 2 minus some little of 1. So this is an improvement on the lower bound for the K5 percolation. And for larger cliques, the picture becomes really different, and we actually disproved the conjecture. So we actually showed that for larger cliques of size of least 6, we can achieve a quadratic time. So we can do it actually really, really slow. Okay, and maybe I'll say some comments about the theorem before I'll talk a little bit about the proof. So interestingly, so clearly what we did for K6 and above could not work for K5, otherwise we would get the same answer here. And interestingly, the reason had something to do with 3-term arithmetic progressions that appears there in our proof for KR when we try to apply it for K5. So we have some 3-term arithmetic progression which we want to avoid. So if we denote by T3n the maximum possible 3-term arithmetic progression free set in the vertex at 1 to n, so the lemma that allowed us to prove the first result will be that the length of the K5 bootstrap percolation is some constant times n times the size of this maximum 3-term arithmetic progression free set. And since we have the known theorem by Behrend that gives a construction actually, but we just need the size that tells us that we have some set of this size, then plugging it here will give us the desired bound. And if someone was hoping that maybe we can find a better 3-term arithmetic progression free set, then of course it's not so maybe better than this, but of course we cannot achieve a quadratic bound using this method because it is known so we have many results by now, but the first I think was wrong, that the maximum possible such set is sublinear. Okay, so using this method will not give us a quadratic bound for the K5 percolation. So this question remained open. Maybe it's true that for the K5 case we have a subquadratic bound. Okay. Are there any questions until now? I didn't look at the chat. Okay, chat seems quiet. Let me see. Any questions? Okay, so let me now talk a little bit about the proofs, maybe. Okay, I will come back to ideas that we talked before when talking about it. Okay, so before we saw that we can very easily achieve a linear lower bound by just considering a collection of clicks, a chain of clicks that intersect with exactly one edge. And we remove this edge that intersects with this click, and then we can infect them one by one, and this will give us a linear lower bound. And okay, and the idea is to do something similar. So what's good about this this idea is that we can really control about on the edges that get infected. We really infect them one by one, and maybe in the K4 case, we saw that other edges got infected, but actually when R is larger, we can really see that these are the only edges that get infected. No new edges get infected, so it really helps us to control the process. But we want something better than linear. So having this just one chain of clicks will not help us. So we somehow want to allow this chain to intersect itself, and maybe to make the process longer. So maybe I will infect these edges one by one, but then maybe I will have other clicks that can get infected that involves some of the vertices of this chain, and then this chain will intersect itself and will allow the process to be slower. So what actually we're looking for? We're looking for, so assume that the clicks that we create, we call them A1 up to AM. So now they're not, in this picture, they're not intersecting themselves, but I trust your mind that you can imagine it, that they can intersect themselves. So I add M clicks, and I want the clicks that the intersection of the click will contain this special edge that will get infected one by one. And I want that this special edge that get infected will belong to specifically to these two clicks, to these two consecutive clicks that intersect, but not to any other click. And why not? Because then if it belongs to a new click, then maybe it can start infecting new edges that we didn't think of, and we lose control. So we really want to make sure that we have this edge and it intersects only, it's a subset only of these two clicks and not of any other click. And we also want to make sure that no other edge gets infected. Okay, so no other edge gets infected, otherwise, once again, we lose control, we don't know what happened, we can start infecting edges and don't know how, maybe suddenly the process will speed up. Okay, so this is what we want to, so this is what we aim to do, we aim to find. So for this, it will be convenient to think of these clicks as hyperedges in an hypergraph. So we have R uniform hypergraph. So each click that will get infected eventually, we will think of it as an hyperedge. And we want to infect these hyperedges, these R uniform hyperedges. So we want to define a hypergraph from G. And the vertices will be the same vertices. And the edges will be those clicks that will eventually get infected. Okay. Okay, so the reason that I wrote it, so KR minus is just KR minus one edge. And of course that if I have, maybe I should have said it before, if I have a copy of KR minus an edge in my graph, then for sure it will become a copy of KR because I have only one missing edge. So every time a copy of KR minus an edge appears in my graph, then in the next step, it will immediately become a copy of KR. So we want to find something of this sort. So let's maybe formalize it a little bit more. So we're looking for a graph with a corresponding R uniform hypergraph, that this hypergraph will have these edges that corresponds to the click that will appear in the graph G. So G is not the starting graph. G will be the graph that we get at the end of the process. And we want that every edge of every hyperedge corresponds to a copy of Kr in this graph. And we want to find two vertices in each hyperedge that intersect, that the hyperedges intersect in such a way that their intersection is exactly these two vertices. For everything until the almost final step, and yeah, of course, we also need to take care of the final step. But the important part will be that this edge is not belong to any other hyperedge. Okay, it belongs only to these two hyperedges. And of course, in the final step, we also need to find some edge to get infected in the final step, which is very simple. And we don't want this edge to belong to any other hyperedge. Otherwise, it might get infected before, and we don't know. And maybe the last thing and most important one, I don't remember why I put it in orange, but I'm sure there was a good reason. Maybe it's a very important property, or maybe it's a property that it's the most difficult to achieve, at least the way I see it, is that every copy of Kr minus one edge that I have in my final graph, of course Kr, but also Kr minus an edge that I have in my graph belong to an edge. So I don't have, during the process, I don't have new copies of K5 minus an edge that appears outside of these hyperedges. So I don't have suddenly some new hyperedge or new Kr minus an edge that its vertices is somehow a combination of these edges. I want all the K5 minus one edge to be inside these hyperedges. This is the only way that I know to control the speed of the process. So this is what I'm looking for. This is what I want to have. And then if I define the starting graph to be this graph G minus this intersecting pairs of vertices, which I will think of as edges when I think about the graph and of the hypergraph, then if I take this and I have all of these conditions, then I know that the length of the percolation with this starting graph will be at least the number of edges, because I can really make sure that I infect these Fi's one by one. Okay, so this will give me a lower bound for the length of the percolation. This is true. This is a lemma. We call it the key lemma. That is true. That is always true, not only in our case. And of course, if we have a lower bound for a specific starting graph, then this will give us a lower bound for the maximum one. Okay, so this will give us a lower bound if we can make sure that we have all of these conditions. Good. So how do I find this kind of graph with hypergraph? This is the big question. And let's look once again on this picture that shows that we have these cliques and they intersect in exactly one edge. And let's pay attention that we have like several special vertices here. So we have the intersection vertices. I call them like the upper ones will be the green, the lower bounds will be the blue, and I want that the edges that get infected will be only these edges. So only between green and blue will get infected. I don't want that blue will infect blue and green will infect green. I want only that the edges that get infected will be between the blue and the green. And I have all the other vertices of my clique they're all, the edges between them are already there. And I want to make sure that no new edges appears, like between two different yellows or yellow and green from here. I really want to make sure that this is a different set. So for convenience of our proof, we will split this. So like we splitted this upper vertices to green and lower to green and blue, we want to split also the rest of these vertices also to two sets. Half of it will be with the green one and half will be with the blue one. So let me write it. So we want to think of the vertex sets of our graph to be the green, the blue, and the yellow. And the yellow I split it to W, which will have the same number of vertices with the green, and the blue, which will have the same number of vertices as the Z, which will have the same number of vertices as the blue. Okay. So the main idea here is that instead of infecting, so we will infect one by one, but we want not to stop after a linear number of steps, we want to continue. So the idea, which I will show you in a minute, was to give a different number of green vertices and blue vertices. And once I do this, I can intersect myself without interfering and creating new unwanted copies of KR. So I want to make here I did the blue. So the blue a bit longer than the green. So let's see how does it look like. Yeah, so these are the hyper edges. So these are the hyper edges, right? All the cycles here are the hyper edges. And yeah, sorry. And instead of considering it only once, so I want to allow it to intersect itself. So I have this xt, yt, xt, yt, xt plus 1, yt plus 1, all the vertices in the middle. So I go over it once, and then I want to repeat the process. So I actually want to take it modulo, here modulo m, and here modulo l. So I want to be able to, for the chain to intersect itself. Let's see how it looks like. Okay, I will show a picture. It will make it clearer. Okay, so we start here, and we have n green vertices and L blue vertices. So the green vertices will end here where the N is, and the blue vertices will end here where the L is. And half of the yellow vertices will be correspond to the green, and half of the yellow vertices will be correspond to the blue. And I start infecting. So this edge is missing, I infect it, I infect it, I infect it, I do it, I do it, I do it. Okay, now I am I'm out of green vertices, but I have more blue vertices. So I continue because I took it mode N. So now I can continue. So now this vertex became the first one here again. And with the blue, I continue. And the only missing edge in this split, because we already infected this one, and this one and the others already appeared inside. So the only missing edge will be this one. So now I infect this edge. And I continue now, the other green will jump. And the yellows, because everything I took from the upper part is mode N. Okay, so I can continue, and the only missing edge will be this one, so I will infect it, and I can continue and continue, and I'm out of blue vertices. So this blue vertex will jump for the beginning. Okay, and now the only missing edge is this one, and I can continue this process. Okay, and then I can do it many times. How many times? So I claim that I can do it, that I can do this thing a linear number of times, and then in each iteration I have linear number of edges that got infected, and this is where I get this quadratic bound. Okay, so maybe another way to see it, maybe a more nice, I don't know, maybe it's easier to see it this way. So I have the green I have n vertices, n green vertices with the corresponding yellows, and I have L blue vertices with the corresponding yellow, and L is much larger than not much larger, but larger than N. And then assume that I start with this hyper edge, which corresponds to a flick, and this is the only missing edge here. So I can infect this edge, and now this will be the only missing edge. So I can infect this one, and I continue this way. I continue, until I come back to the starting point. So this one got infected, so now I can infect this one, and I got back to the starting point. But what happens that in the inner cycle, I go much faster than on the outer cycle. Okay, so this will give me this property that now this edge, this edge will is not exist, and I can continue, doing it linear number of times. Okay, and this will give me the quadratic bound. Okay, so this is exactly what it's here. So let's say that I have all the properties. So I have the hyperedges, and I have the intersection of size 2. Only edges between x and y are missing. All the other edges that I need are there. And I do have the property that this the edge that we infected is not appearing in any other click. And this comes from a number theoretic fact. So we just need to make sure that with this modulus, we didn't mess things up, right? We need to make sure that we always infect, that we keep this property. And this is a very simple claim from a number theory. And we also have the same thing for the last edge. And the most important orange property that it's in orange is that we don't see any other copies that suddenly appear of a kr minus an edge that will speed up the process. And sadly, this is also only true when we do this construction that I explained, when the click has size at least 6. And why is that? So it's not true for r equals 5. It will not work for r equals 5. We already know that. And why is that? So if we have r equals 5, so we have only one yellow vertex, right? We don't have two yellow vertices. And what happens is that assume that we had this click, we had this K5, and we infected it, and we continued like infecting, and at some point we came back to the starting point. And now we have this click, but we have two copies of K5 that intersect in a triangle. And we know that K4, so this will be a K5 minus an edge, because it's two copies of K4 that intersect in a triangle. So this property will not hold in this case, because then we can add this missing edge. So this will not work. And the reason that it didn't work is that because this yellow vertex came together with the green ones, right? Because it was the same triangle in this edge and in this edge. So this yellow vertex is really annoying, and maybe if we don't glue it with the green vertices, then we can do something better. So new plan, let's deal with the r equal 5 case. So let's take 3 sets of vertices and not glue the yellow ones to the green and the blue. So I have n vertices and then L vertices, which is more than n, say n plus 20, and I have the yellow vertices, which is n plus 40. And now I have 3 sets of vertices, and now I do the same. So I have an hyperedge, I have this hyperedge, and assume this is, so once again, I want to infect edges only between the green and the blue. Okay, so I can infect one edge here, and then one edge here, and I continue until I came back to the starting point. Good, so I didn't have the previous problem that I had this triangle that was the same, but I have a new problem apparently. And the new problem that, okay, I continued, I came back to the starting point, then I continue, I do it many times, and I suddenly see this edge. So I have this intersection of 3 edges. Let's see it in a nicer picture. I have this edge. I infected edges, and then I got back to this starting point. I had a new edge here, and then I continue the process, and I have a new edge here. So I have these 3 edges that intersect with each other. And what happens here? So if I look at, for example, these 5 vertices, so I take 4 vertices from these intersections and 1 vertex out of it, and I have a copy of, once again, of K5 minus an edge. Not good, okay? Because then a new edge between the yellow ones will get infected, and I don't want it to happen, because then I cannot control the process anymore. So let's think what is the reason of that. So what causes it? So let's look at one vertex in each intersection. Here I have from the blue, I call it X, Y, and Z. So what do I know? I know that X and Y are in the same edge, right? They share an hyperedge, are in the same clique. What does it mean? It means, so since I know that the Y vertices, the green vertices, had 20 more vertices than the blue vertices, so I know that in order to be in the same hyperedge, then Y equals to X plus 20 times something, some integer, because I rotated it. A is the number of rotations I did. Okay, so I know that I have this connection between X and Y. And Y and Z are in the same hyperedge. So I also know, Z and X are in the same hyperedge. So, and I know that the number of yellow vertices is 40 more than the number of blue vertices. Maybe I switched between the green and the blue, I'm not sure, from the picture before. So I know that it's 40 more. So I know that Z, I have this connection, that Z equals to X plus 40 times something, some integer. And once again, and Z and Y are in the same edge, so I have this connection between them, and together it will, I see that a three-term arithmetic progression like this. And this is what I want to avoid. So maybe if somehow I'm able to avoid this structure that will create this three-term arithmetic progression, then I can do the same idea, but avoiding this K5 minus an edge that suddenly appears there, and because of it, I cannot control the process anymore. So this is now the new plan to do exactly the same, but to avoid this specific structure. So what is the solution? How do I do it? I once again take 3 sets of vertices, I do the same, but this time I don't do it like consequent, I don't take consecutive cliques. I somehow, I give space between them in such a way that will not allow this thing to happen. So if I take xt and xt plus 1 in their edge, so I will not take yt and yt plus 1. I will take yt plus b and yt plus b plus 1. And I will take yt plus 2b and yt plus 2b plus 1, doesn't really matter. And I will take z, I will not take, oh, here z is w, of course. W is z, so I will not take w, I will not take wt, I will take wt plus b. And I will take this b, I will go over a set which I know that doesn't contain this three-term arithmetic progression. And this is like roughly the way I am able to avoid this thing that will create a new copy of K5 minus an edge, and this is where this three-term arithmetic progression pops up in our proof. Okay, so this is the way we found to solve this problem. Maybe there are others. Okay, so questions about the proof or anything else? Good. So okay, so maybe let me just explain a few more words about this this new construction, this new idea of how to take these hyperedges. So I still have. So once again, I have n vertices, n green vertices, l blue vertices, and k yellow vertices. And actually, once I'm doing this, N, L, and K could actually be the same, can all be L, it doesn't really matter. But what I do, I don't take in the same clique X1, X2, Y1, Y2, and W1, and then X2, X3, Y2, Y3, and W2. I somehow spread it, so it will be X1, X2, Y1 plus 2B, Y2 plus 2B, and W1 plus B. And this B, and I go over all B's that are from a three-term arithmetic progression free, and this will allow me to create these chains that will not contain, so these chains that we saw before, that will not contain this structure. I still need to find a way to connect these chains together. And for this, we use some small feature, but the main idea is to create these chains that will not contain this specific structure and to avoid a K5 minus an edge that appears. Okay, so let's conclude. Let's see questions. Okay, so I'm just reminding the definition. So we consider the bootstrap percolation, the age bootstrap percolation. When we have a specific starting graph G0, the length is the minimum number of steps that we need until the process is stabilized, and the maximum length will be just to maximize over all starting graph. And the question of Bollobás was to determine it for K5, and we had some results and some conjecture that it should always be sublinear, and we showed that it's not, that it is not sublinear, subquadratic, and we showed that it is of order of n squared for R at least 6, but for 5 we didn't show it, and the question is still what happens in the K5 case. And another interesting question is that, I think it's interesting too. So we know that for KR, where R is at least 6, what we showed is that it's for of order of n squared, so some constant time n squared, but this constant is not, it doesn't depend on R. So we don't know the dependency of R here, and it's quite clear that there should be some dependency of R here, and we don't know it. So another maybe interesting question will be to determine the right dependency and not have just a global constant for all R at least 6. So to really understand what happens here in terms of R. Okay, so these are two nice questions to continue thinking of, and yeah, I'm done. Thank you.
Thank you very much for a lovely talk, Gal. I'd like to invite people to ask questions. So there are two ways you can do this. Either just say in the chat that you've got a question, or feel free to use the raise hand button. To get us started, I believe Alex has a question, so I'm going to let him unmute himself and ask it.
Great, yes, thanks. So thanks, Gal, for a very nice talk. So I had two quick questions. So one was, what do you believe is the truth for K5?
50-50. Okay, so if I will politely avoid the question by saying something more. No, so if it's subquadratic, it will be, so what I would say that it will be very interesting if there is a real connection between the K5 case and the three-term arithmetic progression. So if and if there is a real connection, then the answer should be subquadratic. And at least from our approach, it seemed like that there is no way to avoid it. Somehow, because of these two reasons, of these three edges that intersect and creates a copy of K5 minus an edge, and also the fact that K5 minus an edge is just two copies of K4 intersecting in a triangle. So if the connection is really, if there is a good reason for the connection, then the answer should be little O of n squared, and this would be very, very interesting thing to see, like these two things that shouldn't be connected, like connect. So I want the answer to be little O of n squared, but I don't know if this is what I do.
That will be nice. My other question is, so in these weak saturation and slow percolation questions entirely make sense for hypergraphs. So for example, for 3 uniform hypergraphs, do you get, could your constructions maybe be tweaked to give slow percolating sets?
Slow percolating sets for,
For K K6-3 or K10-3 or something?
I didn't think about it. Yeah, so the first thing to check will be if this key lemma that I showed before, that the conditions that we want to make sure if they, if we can prove something analog for hypergraphs. The thing, yeah, and this might be possible, maybe, yeah. I didn't think about it, but I think it might be possible just to adjust the proof and make it work.
Thank you.
So I think there are 3 questions that I've had registered so far. So I'm going to unmute Vincent Fenninger and he can ask his first. Vincent, you're unmuted.
Hello. Yeah, thanks for a very nice talk. So I'm not sure what my question is the same as the last one. So basically I want to ask is, when you define the maximum running time, what if we maximize only over the starting graphs that eventually infect everything?
Okay, yes, so this is a very good question. And yeah, so as I mentioned, so the construction that I showed you will not eventually infect everything. But the thing is that it's, okay, yeah, maybe I should have prepared a slide for it. But the thing is that maybe I can take the same construction and then have some gadget that will get infected only at the end and then will magically infect everything else. So it will affect the final answer by a constant factor, but it will still have the same order of magnitude. So I can finish. So just imagine that you do the same construction, just exactly the same, but you keep some vertices outside just for the ending. And then you infect everything. And then once you infected this final edge, then this allows you to infect this new gadget that will help you to infect everything else. So this is possible to make in our construction. So so the order of magnitude will still be n squared for r, which is at least 6. But I'm not sure about the exact constant. But it is very interesting to think of. Thank you. Is this
thank you.
question?
So
Yes,
next, Oliver Riordan, would I like to ask a question? Oliver, you're unmuted.
Thanks. Did you have any kind of, so for larger R, you expect it to go up. Do you have any kind of non-trivial upper bound at all? Could it get sort of closer to a half the constant, or is there somewhere that it has to stop before then? I mean, to n squared over 2.
An upper bound. No, we don't have any upper bound, so we have trivial upper bound of entries. So we didn't even. Our result, we didn't consider anything, but yes, I don't know.
Also, another question: are there interesting graphs other than complete graphs?
Yeah, that's also a very good question. Yeah, so of course, the next step will be to investigate other graphs. There is some works in progress from what I know, like for bipartite graphs, but also other graphs. Yeah. As Alex mentioned before, hypergraphs can be interesting. But, yeah, we didn't consider any other graphs, but it's definitely interesting. Okay, so maybe one comment about it, which worth saying now, because somehow this this length is not, maybe when you're first thinking about it, it might seem like in some kind monotone if you're looking on graph on the same set of vertices, but you have less edges. So it's easier to get infected on one hand, but on the other hand, you need to start with less edges. So somehow it's not clear how, if you have monotonicity at all here, or maybe I would say that maybe you don't. If you consider graph which is not complete, it's not clear that the answer should be smaller, for example, or larger, for example. And yeah, so in this sense, it's interesting to see also the connection between these two ideas.
Okay, Thank you.
Thanks. And then just, so one final question, I think, from Agelos Georgakopoulos. Agelos, you're unmuted, so you can speak.
Thanks. So yeah, essentially Alex asked my question, but I've written it in a refined version of that in the chat. Is it true that for every dimension of a hypergraph, there is an R such that the length of KR to the D, so the complete D regular hypergraph on the R vertices, has the maximum possible length? And how does, I'll type that in the chat as well, how does the minimum such R grow with D?
So do you want to make it a conjecture, or?
I'll make the first one a conjecture. The second one, I don't have a guess.
Okay. So yes. So this is yeah, it's a very nice question and conjecture. We didn't consider hyperclassical, but yeah.
So there's a comment from Oliver in the chat. It looks like the same construction should just work with D separate rings, he says.
Yeah, D separate rings. What's a ring? Like
I can't for some reason. Hang on a second. I'm just.
Yeah, the ring was like your x's and y's. You had your n x's and n plus 20 y's,
yes.
and some co-prime number of z's for a 3 graph. And then presumably you need maybe it's something like goes for R as 3D maybe, but you need 2 vertices of each color and plus the sort of third one to avoid the problem you had with K5. Don't know.
Yeah, I think it might, yeah, should work, but.
So I'm going to suggest that we stop there, and I will stop recording, and we can thank Gal by giving her a sort of traditional round of applause. Anybody who wants to stick around and talk about hypergraphs is very welcome to do so in the gap. So just before we do that, let me say that there will be a second